First of all, it's a real pleasure to be here with so many great customers, great partners. My talk today is about modern ICS monitoring and cybersecurity, modern cybersecurity and operational visibility for industrial control networks. I'm going to talk about first visibility, which is the first step of cybersecurity, and then cybersecurity with three use cases, three of our customers that had very significant challenges and solved their challenges in this area. So first, I'm going to talk a little bit about why is it so difficult to protect industrial control networks. I think most of you know it, so I'm going to go fairly quickly through that section. I'm going to talk about operational visibility because it's the first step. You cannot protect what you cannot see. So many of our customers, every time we show up to a plant, the first question that we ask is, do you know how many PLCs or RTUs or DCSs do you have? And the answer is no, we don't know. That's why we invited you here. And then the third section is about how to provide effective and integrated cybersecurity in a modern age. So very quickly, why is it so difficult to protect industrial control networks? And let me start maybe from the beginning, right? What are we doing? We are providing automation. We're in the middle of what we call industrial revolutions. The first revolution was all about mechanical systems. The second revolution was all about process. In the third revolution, we introduced programmable systems and started the automation wave. And now, in the Industry 4.0, it's defined as 4.0 as the fourth industrial revolution. It's all about connecting system, automating system, bringing intelligence and connectivity into the plant. But when you bring intelligence and connectivity, you have some challenges. Some challenges have to do with the perception of air gapping, and we talk about the intersection of air gapping or segmentation later. Most of the protocols come from the past, from before, and they were not prepared for network connectivity and for shared connections. And then cybersecurity is an extra step that wasn't needed in the third industrial revolution, but it's a requirement in the fourth industrial revolution. So networks go from being separated, segmented, having proprietary hardware, proprietary protocols, proprietary software, into a world where where everybody's using Windows systems, all the protocols right on top of TCP/IP. TCP/IP wants to connect to the rest of the world, and the endpoints of our networks are not really prepared. Our networks' endpoints don't have any authentication. I think Marcelo covered that really well. Don't have any encryptions, have tons of backdoors because they were built in an era where they're supposed to have a one-to-one connection, not to be in a very large shared network that now is exposed to dangerous activity, whether it's human-generated, friendly-generated activity, or malicious activity. So, just like Marcelo showed a little bit of a survey, I have a survey to complement his governance survey. This one is about what are we concerned about when it comes to industrial control networks. SANS is a very large cybersecurity group that does both IT and OT security. It reaches over 300,000 security professionals, although this particular survey or this particular program reached 165,000 professionals. And some of the things that they found out when it comes to industrial control networks is that the majority of the people believe that the current threat level is extremely high in their industrial control network. The current environment, if you add severely critical and high, becomes over 50% of the population believes they're vulnerable and have a high exposure. And then what exactly are you concerned about? The number one thing is how things connect. Whether we have laptops connecting, we have service providers plugging into our networks with their laptops, internal threats, whether accidents or malicious threats from internal people in our companies, external threats, hacktivism. All these threats have to do with our most precious asset, which is our industrial control network, which powers pretty much everything that we do. So the first step, this is where we are. We need to know what we have. We need to be able to visualize all of our assets. And we believe, our company, through our various engagements with partners and customers, that the first step is to gain visibility. You have to know what assets you have, how many assets, what kind of assets you have. You have to be able to visualize your network, understand your network, how is it segmented, how is it behaving. You have to be able to model, do if-then analysis. If I add this segmentation here, what would happen? And you have to understand its vulnerabilities and remediation points. Then, once you have full visibility, which is a requirement for cybersecurity, you have to protect your physical process. The only reason we have an industrial control network is to support a physical process, and that's what makes this network different from any other corporate network. This network is supporting a process, and the malware creators have discovered that in order to be effective as a malware creator or as an evildoer, you have to understand the physical process. So if you're going to implement an effective defense, you have to be able to understand the physical process too. If you do not understand the physical process, then the malware has an advantage over you. So behavioral cybersecurity is a requirement. Rules-based active security is also a requirement. It's not one versus the other. We combine both. Let's do an example. So first, we start with visibility. Some connections happen between your control center and your devices. Some connections happen locally in a plant, and so forth. Some connections actually happen from the outside, and you want to be able to detect and learn about all the different connections that are happening in your network and some of the connections that happen from the outside, whether they're authorized or whether they need to be addressed or blocked. And you have to be able to do that for a very, very small plant out in some region, or you have to be able to do that all over the world. So first, you ought to be able to monitor, you have to be able to detect, and you have to be able to secure. And you need a pane of glass to be able to visualize all this. And like I said, you have to be able to do this in a single plant, or you may be able to do this across a very large series of plants, all from a central connection, all from different management consoles. Some viewers, for example, some users of the system in the plant may care a lot more about OT-oriented visibility. They may care about process improvement, process optimization. They may care less about cybersecurity, or they may care more about the IT, the performance of the network, the health of the network. While some people in the control center may care about overall stability, but also very, very much, let's try to monitor cybersecurity as a whole. So entertaining all three users is also a requirement. Your OT user, who cares about process, your IT user, which cares about the health of the network, and third, your cybersecurity user, which cares about protecting your systems. So let's talk about behavior-based anomaly detection. I talked about how if you want to be effective against malware that knows your process or that is here to learn about your process, you have to be able to protect in the same way. So the first thing that happens in an attack is that you have the initial infection. You need to be able to detect an infection. How do you detect an infection? Well, signature-based is a traditional way of detecting an infection. Most things have a signature. Zero-day attacks do not have a signature. Malicious insiders or compromised insiders do not have a signature. So you need to be able to have both behavioral-based anomaly detection, signature-based anomaly detection, and you have to be able to provide assertions so that people that are monitoring can ask questions about the network. Who has entered my network in the last month? With what protocols and so forth. The second step usually has to do, once you're infected, you have lateral movement, so you have to be able to discover, just like the malware is trying to discover assets and try to know what to infect next, you have to be able to catch that lateral movement and detect it. And again, you need both signature-based and anomaly-based. And last, in a traditional attack, you have the actual harm, where you actually change a pump speed or change a rotation of a turbine. And that also is detected with behavioral-based and anomaly-based. So what are the challenges when it comes to visibility and cybersecurity? So first of all, if you have grown up in an industrial control network, traditionally, IT tools do not work. IT tools tend to be active in the network. They tend to scan or inquire. And one of the #1 rules for us is that you can't be disruptive. You have to be passive deep packet inspection. That's what you need to do in order to be flexible and welcomed in an industrial control network. The second thing is you have to be able to understand that the only reason this network is here is because it has a physical process. So you have to be able to learn about this physical process, understand what's normal and what's not normal in the physical process, and you have to be able to connect with IT systems, right? Everybody monitors security with a SIM, whether it's Splunk, QRadar, Logarithm, whatever you use. You have to be integrated with the rest of IT systems. Okay, so let's talk about the first part, operational visibility. You cannot protect what you can't see. I'm going to try to use case studies from our various customers, and whenever I can, I'll try to mention some of the partners that we're working with. So the first case, network visibility and monitoring. One of our customers, Vermont Electric, they provide and supply electricity in the state of Vermont. Very typical case. We showed up there, and they wanted to have visibility and protection, and the first question is, can you give me a map of your network? An accurate map of your current industrial control network? And the answer is, well, we don't have one. We have this network design that is 5 years old. It has coffee stains all over it. And as soon as you check 1 or 2 IP addresses, you know that the map is outdated and not realistic. So Chris really wanted to have a real-time network visibility tool where you didn't have to rely on manual documentation gathering, where you didn't have to rely on interviewing people. That's not real time. You didn't have to analyze or trace connections manually. You can't really be active in the network because you have a real OT process running in that network that does not want to be disturbed. So you can't really be active. And most traditional OT equipment doesn't support traditional network discovery, network management protocols. So what did he need? He needed a non-intrusive tool that could quickly monitor, discover, report on network health. So this would be a tool, and of course, this is an implementation with Nozomi, where we would first discover his entire network. We go into a process where we start learning about the network. As soon as we learn about a node, we start classifying the behavior of that node. You cannot really see it from there, but the color coding starts happening slowly. And it really reflects the role that the different nodes represent in a network. For example, the blue nodes are PLCs, or slave roles. The red nodes happen to be SCADA masters. We also start mapping the network hubs, network segments. And somebody, Chris in this case, was able to now drill down, for example, into this particular section of the network and examine it better, right? We now understand that this is Ethernet IP, this is Modbus over here, this is the SCADA master, these are the PLCs connected to that SCADA master, so you start gaining visibility into that network. In addition, you can go very deep into the details. You can understand the node characteristics. This is an Allen Bradley PLC. These are the expansion cards. This is the firmware. You also can see the variables, the physical process variables that this particular PLC is controlling. So for example, it could be water pressure, it could be electricity generated, kilowatts, it could be frequency, whatever the physical process is, you also want to monitor variables from here because you want to learn from them, you want to detect anomalies. You also want to monitor links, the health of links. You want to monitor the contents, the files going back and forth, whether they're configuration files, whether it's the ladder logic, a delta between a configuration file and another one. And you can actually have your own alerts. So for example, everybody believes that links are persistent, or a service provider may be telling you that this particular link is persistent between this remote site and the control center. And it may not be the case. You may be charged more. You may be able to address the lack of persistency. Or, for example, everybody believes that my site is air-gapped. The only connections between my site and the outside world is this particular switch that everybody goes through here so I can inspect them. And that may be true at one particular point in time when you checked or when you installed the switch the first time. After that, you never know. So you want to be able to monitor if it's true that your site is 100% air-gapped or everything is going through the sanctioned gateways. So that was the first case study with Vermont Electric. I'm going to go into the second case study. This one is particularly it's a pleasure for me to talk about it because this customer is, Enel is our largest customer today. It's competing with other customers, but today is our largest deployment. It also has expanded into Brazil. So we have done 2 implementations with Enel in Brazil, one in Fortaleza. I can't remember where the other one is. And it includes 2 great partners of Nozomi. One, IBM. We've done an integration with Curator. And the other one is Siemens. We're doing an integration with Siemens in some of the substations to have our products in the same box. So Enel wanted to have not only full visibility of the network, but they also wanted to know specifically asset information. They need to have an accurate list of assets and understand the vulnerability. What are they exposed to with those assets? So the standard approach, again, very similar. You have a dichotomy when it comes to asset management. Either you spend a lot of time manually gathering information, going to every site, documenting PLC information, trying to get it from your SCADA application, from one vendor, from another vendor, manual work, or you have an active solution. As you can see here, I really haven't listed an active solution because active solutions are really not allowed in OT. You cannot be active. You cannot be asking PLCs for their diagnosis information if you're not from the same vendor. So basically, you have this problem, manual or impossible. And what Enel really needed was a non-intrusive tool to passively discover all the assets, passively gather information about those assets, and understand their vulnerability and so forth. So very similarly, once the network has discovered the different assets, you can have a list of all your assets where you have operating system, if those are Windows servers or endpoints, or firmware, if those are PLCs or RTUs or whatever they are. You can have vendor information, product serial number. You can dive into the details to learn vulnerabilities. So once you know that, hey, this is an Allen Bradley PLC with firmware version 18.0 and 2 additional cards, you know that there are certain vulnerabilities associated with that patch of software that you have, and you may decide at that point if you need to upgrade that patch or not. But at least now you know, and you're enabled to perform risk management tasks. Just like vulnerabilities, you can, as I mentioned, know the firmware version, product name, hardware components. You can layer your assets in the way they're segmented. This particular segmentation is called the Purdue model. So you can order your assets by Purdue model or by any segmentation that your company enforces. And now moving on to the third case study. Once we have provided the visibility, once we have discovered assets and tracked them and keep them in an inventory, of course you now want cybersecurity protection. DIWA is another great case of ours, and of course I now remember that my partnership with Siemens is really here, not in the Enel case, but this is the largest distribution of electricity in the United Arab Emirates. If you go to Dubai, the electricity being provided is protected by Nozomi. And what they wanted to do, because they are at the forefront of attacks, specifically because they have an event coming up, the Expo 2020 is going to be in Dubai. So they needed the extra protection. They were looking for a cybersecurity solution to completely protect them against advanced malware. So the standard approach is try to air gap your plants. And when you have a distribution center with substations all over the place that need to connect over wireless, that suppliers go and install stuff all the time and upgrade stuff all the time, it is impossible to believe that air gapping really works. If anybody believes that air gapping works, I'm sorry. I'm here to tell you that it doesn't work. The only people that truly implement air gapping are very selected sites in the military and very selected sites in a nuclear environment, because you require a special discipline to truly air gap your plant. So if you're not in the military and you're not in a nuclear facility, it's very unlikely that air gapping is not going to be a realistic answer for protection. So they needed a non-intrusive OT solution that understood both process-oriented or behavior-oriented techniques to stopping and detecting attacks, as well as signature-based approaches. And signature-based approaches are really effective through the entire life cycle of an attack. As I mentioned, they're really effective during the infection phase, really effective during the discovery phase, and really effective during the attack phase. But sometimes, if you have had researchers around the world synthesize an attack, for example, in Destroyer, or for example, Black Energy, if those attacks have been synthesized by some of the researchers, it would be silly for us not to tell you that this is an attack that has a signature, and by the way, this behavior is associated with that signature. So we are the only solution in the market that combines both behavioral-based anomaly detection with signature-based anomaly detection. So we use JAR rule, packet rules, and we also allow assertions. For those of you who are inclined into doing threat hunting, we allow you to do threat hunting with our tool. So for example, we detected an incident here. An incident is a grouping of alerts that have the same causality. So the incident, for example, is detected. A new communication is an incident that groups many alerts. And now we provide you the incident details. So for example, the first alert was a rogue MAC address, right? That's a clear telltale sign of network spoofing. Somebody spoofing your network. Second one, a new connection between somebody, one node and another that was outside of the learning. So the learning phase has already concluded. We know how your process works. And these are two nodes that we're not supposed to talk to each other, right? So we detected another alert that is now related to the first alert. And the next one is, well, it's using a protocol that is not expected, right? Malware doesn't know really what protocols are you using, so they try to use generic protocols. And then they try to program your PLC, in this case, in a production run. So we group those alerts. We understand they have the same cause. They're totally related, and we present it to you as a single item. That's extremely important for many reasons. One, we're using machine learning and artificial intelligence techniques to learn your process, number one. That's the base of behavioral-based anomaly detection. Two, we're using the same techniques, machine learning and artificial intelligence, to group alerts together that have the same causality. And this allows you, for example, if I were to go into your network and do a scan of your entire network, and you had a traditional anomaly detection solution, if you have 1,000 nodes, you're going to get 1,000 alerts. And if you have a security operation person that is now flooded with 1,000 alerts, that person's not going to know what to do for the next hour. So operator effectiveness, security operations center effectiveness is key. So correlating all those into a single incident that says, okay, somebody scanned your network, and here are the 1,000 alerts that are related to this, but now you're seeing one event is super effective when it comes to security efficiency, right? And of course, if you want to do forensics, you may have gotten this alert at 4 p.m. in the afternoon, but the alert happened at 8 a.m. in the morning. You want to do a full analysis. You want to be able to see what happened 2 hours before and 2 hours after, or 10 minutes before and 10 minutes after, even though this already happened 12 hours ago. So you want a solution that gives you the complete forensic analysis. Last but not least, you also want to monitor communications, right? So we talked about SMB communications in your industrial control network. That usually are configuration files changing, moving back and forth. In this case, you want to be able to do signature-based analysis. You cannot see it here, but this alert is telling you that this node sent to this node a packet that included the WannaCry signature. So 2 of your Windows machines are sharing the WannaCry payload. So you're about to be hit by WannaCry. So you want to have this type of alerts that are well known in the industry also apply to your industrial control network. These type of solutions tend to live deep in the network, so they are usually in between where your PLCs and your RTUs exist and the control network where your supervisory and control infrastructure lives. So you want to be listening to all this traffic. You want to go through a learning phase. You want to learn the physical process. You want to make sure that the solution works whether this site is super, super small, like a substation in the middle of the desert, or super, super large, like a network of 4 or 5 refineries together, sharing a common network with thousands of nodes. And for those distributed infrastructures, you want to make sure that you are able to connect with your SOC or NOC. You may already have a SIM. As we all know, SIMs are all about logs. We really don't have logs with context in the industrial control network, so you need context provided to the SIM. If somebody sends a SIM an alert that says, your furnace is at 400 degrees, that doesn't mean anything to a SIM, right? A SIM has no context with your industrial process. You need to be able to tell the SIM, the furnace is at 400 degrees, and that is abnormal for this particular phase in the process, and it's outside of the learning. So the SIM can now start incident response with context. I think that covers the last use case that I had for you. Let's see. Perfect. Now, if you don't mind, I'm going to tell you a little bit about our company, Nozomi Networks. Nozomi Networks has been around for 5 years. We're a young, growing company. We have deployments in 5 continents. Thanks to Enel, we have now references here in Brazil. We have over 220 deployments worldwide. These are all separate customers. We have 250,000 industrial devices monitored and protected. And we serve the verticals, of course, that rely in industrial control networks for production, revenue, etc. Our product's called SCADA Guardian. I'm doing demos of the product in the next room. It's an appliance that connects to the industrial control network passively. It can be deployed as hardware, physical hardware, or as a virtual machine. It connects to the industrial control network passively. That means span port, mirror port, network tap. And then once it's connected, it starts learning. It does deep packet inspection. Not just level 1 through layer 4, which is what most people that do deep packet inspection do. Layer 1 through layer 4 tells you who's connected to whom, how many sessions, what protocols. But we go all the way to layer 7. So we actually capture the process level commands that are flowing in your network. And we learn the behavior of your network. We learn if the process has phases, or is it a batch process, or if it's a continuous process. We study the interrelationship of all the variables at every stage in the process, so we know when something is normal and something is not normal. This is learned behavior. These are not parameters. And we use artificial intelligence techniques to create behavioral models for what every PLC and what every variable should be doing at every stage in the process. So this creates an anomaly detection engine that has very low levels of false positives and very low level of false negatives. And we use all this information to provide anomaly detection, asset inventory, network modeling, and so forth. Another way of looking at our product here is to look at a deep packet inspection and protocol analysis layer, which is the bottom layer. This is where we understand the hundreds of protocols that exist in our industrial world. Modbus, Profinet, DMP3, hundreds of protocols have protocol parsers that live in this layer, and they can be added modularly very easily. Then you have a real-time process analytical engine. This is where you have the learning of your physical process that happens over time. And you can think of this as an in-memory database of everything that has traversed the network that can answer ad hoc queries in real time. So anything that you could possibly ask about what has traversed your network, you can answer. TCP/IP retransmission links at 10 a.m. You can get an answer. Malware detected, you can get an answer. Level of water in my reservoir are 4 a.m. You can get an answer. If the information has flown through your network, if the information has traversed the network, this engine can give you an answer. And then, of course, we have our network visualization and modeling, which you saw a few screenshots of, our asset inventory. Our asset inventory was tied to our vulnerability assessment, so now you can see vulnerabilities of your OT devices and perform risk management in OT, which has never been done in an automated, passive fashion. And of course, I talked about anomaly detection engine. And I really didn't talk about our dashboard and reporting capability, but you can create a report and a dashboard about everything that has happened in the network. You can create an OT dashboard to talk about process efficiency. You can create an IT dashboard for network health. You can create a cybersecurity dashboard for attack and SOC monitoring. And then, of course, the central management console is very useful for very, very large deployments where you have hundreds of SCADA Guardian appliances monitored from a single location. All the information is aggregated for distributed monitoring. And you can also do remote access. From a SOC or a NOC, you can go into a very far remote facility and see what's going on there. That is all I have.